Hello there, I'm Miro and we will continue now with the Renewable Energy Technology course, the lecture on geothermal energy. We will conclude the lecture with the last section, the third section here, about electricity generation from geothermal sources. Just a quick reminder of the basic principle of extracting geothermal heat and converting the energy into something else. We would certainly rely on water or steam. Through the production well, water is being pumped up to the surface. Then its heat converted to electricity in a typical power plant. And then definitely the goal should be to re-inject the remainder of the fluid back under the earth into the hot rock, so the reservoir sustains its natural water flow. There are different types of geothermal power plants, and we can divide them in the way they treat the steam. First of all, the easiest way would be if we have dry superheated steam. We can call it a direct expansion or just dry steam plants. They are though very rare. Single flash and double flash steam cycles are regularly used for the bulk of power production technology out there in the industrial field. Binary cycles, basically organic Rankine cycles, are also applied, and they hold a promise for a much wider application in the future. Any kind of mixed or integrated arrangements of each of those together, or in a hybrid arrangement, let's say with fossil fuels integrated with geothermal power plants or solar heat integrated with geothermal, are also possible and have been attempted. The most important value of geothermal power is that it is not prone to intermittency the way other typically solar-based, or let's say the more common renewable types of energy are. Geothermal power will be certainly a base load type of power, completely dispatchable, able to be produced anytime, with availability close to 100% as long as the technical availability of the power plant is close to that value. Completely stable and reliable, and again, able actually to sustain a modern electricity network as a baseload power plant. Now, it's a completely different issue that geothermal plants cannot be too big for one unit. And we don't have time actually to define those sizes, but you can deduct these values by just looking at the statistics and the types of power plant arrangements. A short historical note. It all happened comparatively soon, not too long in history, even if geothermal heat has been used by humans also long ago. Hot water springs as for spa purposes, for balneology, have been used already from the times of the Roman Empire and ancient Greece, and even further back in time. But regarding industrial use of geothermal heat, it happened actually somewhere in the 19th century, first in Italy, where this particular exploration site at Larderello started to use hot water to support an industrial process extracting boric acid exactly from the water coming out from the geothermal site. In the beginning of the 20th century, a local prince invested into, an experiment. That's the first pilot field test, simply coupling a steam piston engine to the steam source. Now, there is dry steam available in Italy and Larderello, and running a small dynamo of not more than 10 kilowatts. A few years later, a bigger power plant was installed, and now there is multiple hundreds of megawatts being utilized and constantly running there. The dry steam plants, or the direct expansion approach, would simply rely on having dry, supposedly superheated steam coming up from the earth. Typical parameters, somewhat around 200 degrees, comparatively high pressures. So this process needs a very pressurized reservoir sealed under a cap rock where the water evaporates naturally from the hot source and comes to the surface as steam. Simply the steam is drawn from the production well, filtered and expanded directly in an energy conversion device. Then condensed back into liquid and should be pumped back to the source. Good choice, but unfortunately there are very, very few such fields. One of them is the field in Italy, in Tuscany. Another one is the geysers in California, another very famous spot. And there are a few other smaller fields in Indonesia, the Philippines and Japan, but not any more that are known of. The single flash steam cycle is the typical choice for resources that present themselves as hydrothermal. Hot water with steam mixed at different proportions. The hot water is drawn from the production well and then simply flashed. We can call this step a flash separator or a flash chamber or a cyclone or a throttle. The water is sharply decreased in pressure, which actually separates the fluid from a small amount of steam. The steam is then expanded in the usual way through the energy conversion device and condensed back, mixed with the liquid part of the flash and injected back through the injection well. This is the most popular geothermal resource application. The way we can represent the flashing process in a TS diagram is approximately this. Starting from point 1, the flash process is throttling at isoenthalpic line. The enthalpy stays more or less the same. While we lose pressure and temperature to a certain extent, we sacrifice those in order to separate the liquid flow into saturated liquid and a smaller amount of saturated vapor. The vapor is being utilized for the expansion. The liquid is being returned directly unless there is some direct use of the heat to the underground reservoir. It is difficult to deal with the flashing process because the fluids coming in or water from the underground will definitely contain salts and gases. Many of those will actually remain in the steam flow and need to be treated somehow, catched, entrained in some physical or chemical processes and returned back to the main liquid flow, not released to the atmosphere. The typical conditions are approximately 150 degrees Celsius, preferably more than that. And after the flash, it's just a few bar of pressure that is being utilized in the expansion process. The double flash steam cycles are simply trying to improve a bit more on the single flash process. They rely on the same hydrothermal resources at the same starting temperature and pressure, simply applying 2 steps of a flashing process instead of only 1. There are 2 flash chambers, the second one drawing the liquid remainder from the first flash process and flashing it again to a much lower pressure. All of the flows are mixed in the end and pumped back as liquid to the injection well. Generally, as a rule of thumb, a second flash step would improve approximately 15 to 20% in the best case of the power output. That's good enough to justify the investment. And usually only 5% of additional costs can be expected for the second step of flashing. In a TS diagram, it can be represented in this simple way. Again, starting from point 1, first step flashing, creating liquid and a small amount of vapor, which is being expanded in one of the expansion devices. Second flash from point 3, taking just the liquid from the first flashing chamber, to point 6, creating saturated liquid point 7 and a small amount of saturated vapor, which now is being expanded in the second stage of the expansion device, which can be one and the same steam turbine, simply taking in steam input at 2 different pressures and driving maybe the same electrical generator in the most cases. The challenge here is that definitely if there are some gases and salts dissolved in the geothermal fluid, they would certainly appear in the steam, because now with the second flash we reach much lower pressures, much colder, lower temperatures, and those gases will need to be treated somehow. They should not be emitted to the atmosphere. The optimization here is that if we had, starting from the same input condition, one single flash will provide certain power output, but if we divide it in two, and why not even more, 3 flash steps, we can actually generate much better mass flows or higher mass flows of steam, totally summed for the different flashing steps, thus generating a bit of more power. A third flash step can be added and is or has been attempted in only a few power plants. It is then difficult to justify economically. Binary plants are also called indirect cycles. In the easiest example, if we draw pressurized fluid from the production well, we might like to avoid completely to flash it. Keep it liquid, simply extract the heat, not just for direct use of heating, but for a power process, and then get rid of it or dispose of it immediately towards the injection well. No flashing, no release of dissolved gases, no troubles at all, except corrosivity may be involved with salts in the geofluid. There is a secondary fluid of any sort, able to take the heat, evaporate, and then being treated in the usual way through an expansion device to produce power. In the easiest example, this could be a secondary loop of pure, supposedly much better quality water. However, water steam are not good for very low temperatures, and the binary plants, in most cases being based on organic Rankine cycles, mostly are being applied to comparatively low temperature sources. As a rule of thumb, binary plants are very suitable for geofluid temperatures below 150 Celsius, sometimes even below 100. Certainly, water steam is not the best choice for a working fluid at those conditions. There are usually some hydrocarbon fluids that can be selected, or some a bit more complex hydrocarbon derivative with halogenic components and so on. The easiest examples are the isobutane or the propane fluids, having this queer type of TS saturation dome in the TS diagram if we compare it with common water, or even ammonia, which can be used also in mixtures with water as another sort of binary plant. There are many binary plants operating almost a third of the installed capacity in the world, but they actually generate a very small percentage of the total power output from all geothermal power plants in the world. Theoretically, they have no chance to be very efficient, because just the Carnot potential of using a geothermal heat with 150 degrees Celsius or even below that is very limited to 20-something%. So the actual output or efficiency of the binary plants very often lies around 10%, very low value. They though can be very suitable for combined heat and power applications, or in any kind of integration options with flash plants or with additional heat input. This is one example of the lowest temperature heat source being used in a geothermal application in Alaska. The binary plant is using a refrigeration fluid, pretty much the same found in home refrigerators and very often in automotive air conditioning systems. The hot water coming from the production well is, well, here slightly above 150 Fahrenheit. This is approximately, well, a bit below 70 Celsius. Very low temperature. It is useful simply for direct heating, and this is indeed a spa complex there. However, a small pilot binary plant is being installed, and this is the breakthrough of low temperature utilization for geothermal fields. Many such can be installed elsewhere in many hot springs. However, the power production efficiency, of course, is very limited. Now, in this case, below 10% electrical efficiency. If we look quickly at the investment costs typical for power plant applications, it is a quite even actually breakdown in the different systems. Still, the main hardware, the turbine with the electrical generator, condenser, cooling system, auxiliary systems for the steam plant, they take the lion's share of all the costs. But then there are also the engineering, procurement, the actual building, the civil works for the plant and so on, and also the maintenance. The maintenance costs in the geothermal case usually are very small, pretty much similar to hydropower applications. Compared to the major cost is the initial investment. However, the costs are not so dramatic in this case, and making some measurements or taking data from the existing geothermal applications, we can see that actually the costs are quite in comparison with the common costs for power production from fossil fuels or from other, the most advanced renewable energy-based applications. You can look at those figures on your own. There's a lot to explore actually deeper here. Just let me show you very quickly that the typical learning curve for geothermal power, both with time and with size, actually brings costs down to somewhat 10 US cents per kilowatt hour cost of electricity, or even far below that level. Very competitive with any kind of contemporary power production. Very short review now on a worldwide development. This is a nice comparison of the available number of plants worldwide and their total power output. There are many, even if limited in location, dry steam power plants. There are many more single flash and double flash systems generating the main share of power production based on geothermal sources. Many also binary plants, though generating only a small fraction of the total power. Any hybrids or integrated systems are also possible and should be encouraged. Quick review now of the geothermal power plants around the world. You can look at that figure on your own. Let me continue quickly to the summary and underline once again that any kind of steam cycle can be used. However, we need to adapt it to the temperature and pressure level of the source, usually dealing with steam or in most cases just hot water coming out from the production well. Single and double flash systems are the mostly utilized because the available resources match very well such kind of applications. Binary cycles exist and are being run in many cases. However, they are usually low productive. Despite the large and quite scary initial investment costs, geothermal power is pretty much competitive in modern times with any kind of conventional or other type of established renewable power generation. This was all from me on renewable energy technology course and geothermal energy. Thank you and have a nice day.